I'm Liang from East China Normal University. This work is collaborated with Professor Chang from National Yang University and Dr. Yu Mao from City University of Hong Kong and MBZUAI. And the first author of this work is my PhD student, Wentong. He has been go to company and get a job. So I'm here to give this presentation. This work is about a design on mobile device, how to first launch the application used on a parallel memory reclaim scheme. Okay. So I will go to this talk in 4 parts. The first one is background. Second one is the motivation of the design. And the third one is how did we design the parallel memory reclaim scheme. And the last is evaluation and conclusion. Okay, so this is the background. As you know, the memory capacity is growing during the last 10 years from 8 gigabyte to 12 gigabytes. But from the slides, we can find the application memory footprint is growing much rapid. Okay, so there is a big gap between the memory capacity growing and the application memory footprint growing. So this big gap should be satisfied by the design of the operating system. So there is a very important component in Android system is the swap system. It is designed to relieve the memory pressure. So in current Android memory reclaim system, there are 2 types of memory reclaim method. The first one is implemented in the framework layer. It is called low memory killer demo. And the second one is implemented in the Linux kernel. It is called kernel memory reclaim method. Okay, so let us check what is low memory killer demo. It is designed to release the memory by kill the application. And the memory reclaim scheme, or also called memory swap and directory reclaim, it is designed to reclaim the pages of memory by page shrinking and page writeback from the main memory to the storage. Okay. In the left part, the left fig of this slide, you can find the reclaim path of memory reclaim. It include page shrinking and page writeback. These 2 steps. So we want to check what is the problem for this path. Okay. So in order to understand the issue for this path, we have done experiments on several real products, real mobile devices, including Pixel 6 Pro, Pixel 5, and Redmi Note 11. From our experiment, we found the low memory killer daemon is frequently triggered. It is called to kill the application, and then we need a code launch to start up the application again. So each will introduce a long application response time. Okay, so we can find the low memory killer is not a good choice for memory reclaim. So we need to use the kernel memory reclaim process to release the memory pressure. So we first studied the issue for kernel memory reclaim process. We can find in these slides we show the reclaim throughput of application for these 3 mobile devices. From these slides, we can find the reclaimed throughput is quite low for these 3 mobile devices. Okay, the maximal throughput is only 120 megabytes per second. But our application memory footprint requirements is much higher. It's in several microseconds. It's required around 1 gigabyte. Okay, so this is a big gap. How to speed up the reclaimed throughput to match the memory footprint requirements should be solved. So we first check what is the bottleneck. Is the I/O path a bottleneck, or the I/O device is the bottleneck? Okay, so we first check the device, the storage device, to check whether it is the bottleneck. We have done I/O evaluation on these 3 mobile devices. We found that the storage of mobile device provide a quite higher throughput compared to the the reclaimed throughput. Okay, so the maximal throughput for the storage is around 1 gigabyte, but our reclaimed throughput is around 100 megabytes. So we believe the I/O bottleneck should not be the storage device. It should be the memory reclaim path. So we further check the latency for the I/O reclaim path, and we found that these 2 steps take the majority of the latency. The page shrinking step take about 50%, and page writeback take another 50%, and the storage only take a very little part over the for the whole latency. So we further do experiment to understand what is the problem for the page shrinking and what is the problem for the page writeback. And we found that for page shrinking, it is quite inefficient. We checked the number of reclaim we need compared with the number of reclaimed page. Reclaimed page. We found a big gap. The red line is the number of page we need to reclaim, and the blue line is the number of page it is reclaimed. There is a big gap. So the page shrinking process is quite a big issue. Okay. So the second step is about the page writeback. It's first need to unmap the page in the memory and then write back to the flash memory. And we found that the unmap process and the page write out step also quite asymmetric. Okay, so these 3 issues in the memory reclaim path is the big challenge for optimize the reclaim throughput of the storage. Okay, the first one is a sequential execution of these 2 steps. The second issue is the inefficient page shrinking, and the third step is internally block the page writeback. So we propose a PMR to solve this issue. PMR is designed to parallelize these 2 steps with 2 solutions. The first one is we designed a proactive page shrinking method. The second one is a storage-friendly page writeback. Okay, so let us go to detail for this framework. We first decouple the page shrinking step and the page write step, or by adding a separated demo, and then we write back the unmapped pages by directory claim or kswapd. So for the first one, we propose the proactive page shrink. It's decouple page shrink step and the page write back step, okay, using an independent demo, okay. Then we maintain a victim page list, and we use page shrinking watermark to make sure there are enough pages in the for write back. The second step is storage-friendly write-back. It is designed to unmap the pages in application-aware, and then we batch these unmapped pages to the storage. So we can find that we can combine the unmap and combine the write step. So we have done experiments to show the advantage of this work. We have evaluated on three mobile devices, and we have installed 36 applications and evaluated with 5 schemes to show the advantage of the PMR. The first experiment showed that we have significant performance improvement. Compared with the original memory swap scheme, we have 43% improvement for the latency. We also have a good compatibility with existing work. We have combined the PMR with a recent work fleet. We can find it can further reduce the latency by 38.9% compared to the fleet scheme. Okay, so we also check the reclaim throughput improvement. It is almost double the peak throughput for reclaim, and also the storage device utilization is also significantly improved compared with Pixel 5, compared with between Pixel 6 and Pixel 5. We have also done sensitive study to find the sensitiveness for the design for the ideal pages in the victim page list and the size of the location-aware page on map. We can find these two parameters is kind of some sensitive, but it can be designed adaptively. Okay, sorry. So this is the conclusion of this work. Okay, we have identified the 3 critical issues for the reclaim paths, including the sequential execution of these 2 steps. The second one is inefficient page shrinking, and the last one is the blocked page write back. Finally, then we designed the PMR design with 2 components, and our evaluation on real device show the advantage of this work. Thanks for your listening.